Our next speaker is Professor Partha Talukdar, who is currently a staff research scientist at Google Research Bangalore and is an associate professor at the Indian Institute of Science, Bangalore. His research interests are in natural language processing, machine learning, knowledge graphs, and more recently has focused on graph-based learning algorithms. So today, Partha will talk to us about knowledge-infused deep learning. Partha, it's all yours.
Okay, good. Can you hear me? Okay.
Yes.
Hopefully you can hear me and see me as well.
Yes.
Okay, great. Thanks Arun and Ravi for having me here. And I hope everyone is staying safe and healthy. So in this talk, I would like to present like the importance of knowledge in learning, and in particular in deep learning. Most of the work that I'm going to present, or all of it actually, was done in my research group at IISc Bangalore. And only towards the very end, I'll just have one slide on what we are trying to do at Google Research within the NLU group. Okay. So just as a motivation, I mean, the thesis for a lot of our research is motivated by the fact that background knowledge is key to intelligent decision making. So I have a canonical example for that. For example, say you are trying to build a natural language understanding system that's like going to read the news and then summarize it for you. And such a system comes across a statement like, State Farm stocks tumble along with Berkshire Hathaway. So in order to make sense of this particular sentence, we utilize a lot of knowledge about the world. For example, things like so there is a concept called company in the world, two of whose instances are mentioned here. So one is State Farm, the other one is Berkshire Hathaway. There is these company stocks are traded in a stock market, and then there is price volatility associated with them. So all of those extra knowledge are not present in the sentence itself, and that's by design of language, because we want to use language for communication, and we utilize a lot of that external knowledge to interpret this even a given sentence. But even if you had all of that extra knowledge, why there might be a correlation between the stock prices of these two companies, so that's still not clear. But if I show you some background knowledge of the form here, so Berkshire Hathaway is mentioned here. They have a subsidiary called Heinz, which is insured by State Farm, which is also mentioned in the sentence. Then one plausible explanation for this correlation could be that Berkshire stock prices are down because something bad happens to its subsidiary Heinz, and the losses of Heinz are going to get consumed by its insuring company, State Farm, right? So hopefully our interpretation of this particular sentence is much deeper now compared to, say, 30 seconds before, when we didn't have this background knowledge organized in the form of a graph to augment our interpretation and analysis. So this is a type of graph, fragment of a much bigger graph that we call as the knowledge graph, where nodes are entities and objects of interest, and the edges are basically the relationships that connects those entities, right? So hopefully this gives you some motivation why having this kind of external knowledge could be useful in doing these kind of various types of intelligent decision making. So the thesis behind the talk is that deep learning augmented with external knowledge in the form of knowledge graph could improve performance. So something like DL plus KG is better than, say, DL on its own. So that's kind of like the central thesis of the talk, and I'll try to give you various evidences and flavors for this going forward. So I will have a much broader interpretation of knowledge. So what we talked about so far is an instance of factual knowledge, where we have these entities and relationships connected with each other. So that's what are traditionally called as the factual knowledge graph. But then there could be other types of knowledge as well. For example, syntactic knowledge, right? So given a sentence, you can run things like dependency parsers or constituent parsers and get some sort of internal syntactic structure of the sentence itself. There could be other types of knowledge as well. For example, temporal graphs, like different events and how in what order they happen. For example, this blue event happened before this, like, say, brown event, or these two, like, purple events, like, happens at the same time. So things like that. This could be like additional types of knowledge. So all of these, like, the unifying characteristics among all of these are like different multi-relational graphs. So you have a graph where you have nodes and, like, different types of edges connecting and representing relationships among them. So I'll be interested in collect with some abuse of notation. I'm going to call all of these things as knowledge graphs, as kind of like a unifying term, and be interested in how we can utilize this kind of external knowledge of various kinds into deep learning. So this is the overall plan. So I will first, so if you have some sort of like an unstructured data, first we'll look at how you can build even these kind of graphs. I'll not go into the details of this, but I'll leave you with some pointers to additional papers and tutorials that you can go and look at. In the second part, we'll look at, given this type of graph, how we can embed those graphs in some continuous dimensional space. And then in the third part, we'll look at how these kind of graphs and the embeddings could be used in some sort of like a deep learning model, right? So that's kind of like the overall plan. And I'll be spending most of my time in the part 2 and part 3 in this talk. So, so the NEL system is, so which stands for never-ending language learning, is an example of an effort towards like to go from these kind of like unstructured documents, which are just like documents, emails, web pages, and all, towards building a knowledge graph, some sort of like multi-relational graph structure. And what you see in front of you is actually built by this AI agent called NEL over about like a 10-year period by reading web documents on a continuous basis, right? So here you see things like Toronto Maple Leafs is a hockey team. They won Stanley Cup and their hometown is Toronto, right? There are a lot more details on how this type of graph can be automatically constructed in this way. So you can actually go and visit this URL, rtw.ml.cme.edu, where kind of like it gives all the providence and you can browse the graph. And I was also part of this project at CME. So if you're interested in learning more, you can read this Communications of the ACM paper from 2 years back, from 2018. And we have also given a bunch of tutorials on this topic to learn more about the general problem of never-ending learning. So how you can build learning agents that can learn over not just like minutes and hours, but over months and years. And then how those kind of a framework could be utilized towards building this type of graph. And here are 2 pointers to tutorials at ICML and KDT. So that's all I'm going to talk about, and just point to papers on these and tutorials on these topics. If you're interested, I can pursue further about the construction part. So now moving on to the embedding of these graphs. So you can broadly think of as like 2 high-level ways of representing knowledge, and one is around this kind of like a symbolic representation in the form of multi-relational network that we have been talking about so far, and other complementary way of doing that is through these dense representations, right? So where each node in the graph, for example, GM is a node here, so that node actually becomes like a point in some sort of high dimensional space, right? And then you can think of like representing both the node and the edges or the relationships that connects them as points in this kind of high dimensional space. So, and each one of them have their own strengths and weaknesses. For example, doing inference over these kind of dense representations tends to be better, higher accuracy. But usually these are learned by deep methods, but they are not always very interpretable. But in contrast, like, if you are doing inference, or like, how, say, two nodes in this particular graph are connected or could be connected, and if you could explain that by using existing paths in the graph, then that's much more consumable to humans, right? So we kind of like think of this as like two ends of the spectrum, and we are interested in how we can go back and forth between these two types of representation. So the next few slides, or even in this talk, I'll give you multiple evidences of how we can take this kind of like a graph and then get these types of representation. So over the last couple of years, there's been explosion of work in this space, which is more broadly called as the knowledge graph embedding, where given tuples of this kind, Barack Obama, president of USA, where the first entity is called H, which is the head entity, president of is the relation, and tail is the country, USA. So what you do is basically you learn these embeddings, HR and T, in some sort of vector space. So usually these objects are like vectors, and then you employ various types of constraints among these entities. For example, you could say that this relation vector, which corresponds to president of, should translate the head vector, which is the Barack Obama, towards this tail vector, which is USA. Right? And then you can pose this as like a loss function. So you want to minimize this H plus R minus T, and in that process learn these embeddings H, R, and T. Right? So embeddings are these kind of vectors, and then there are a slew of other methods which take alternative forms of representing these different entities and relationships. Some of them represent them as matrices, others as tensors, and so on and so forth. But all of them have this unifying structure that they all do some sort of triple scoring, right? So for example, a function of this type, like f, taking R, H, and T as basically arguments, and you want to increase the score on the positive triples and then decrease the score on the negative triple, right? So Barack Obama, president of USA, will be a positive triple, and then Barack Obama, president of, say, India, will be a negative triple, right? So you want to increase increase the margin between these two types of scores. So so I'm not going into the further details of how all of these things could be done, but there are multiple tutorials that are available on this topic. So if you're interested, you can go and look into them. So I'll just highlight maybe one task, which is a very important one, how we can utilize these kind of graph embeddings to make some progress on this problem. And the problem is about canonicalization. So this is based on work that was published in WWW 2018. So given, say, noun phrases of the form Barack Obama, Mr. Obama, Mumbai, Bombay, Madrid, we would like to figure out that Barack Obama and Mr. Obama is one node, Madrid is another node, and Mumbai is Bombay is another node, right? So what kind of signals we could utilize? Maybe by doing some sort of extractions and looking at text, we find that this Barack Obama noun phrase and this Mr. Obama noun phrase are related to the same entity called Michelle Obama, right? Even though this kind of surface forms that's there in the text, one says married, and the other one says is married too, even though they are not exactly the same, but they are kind of quite similar. And since they are related to the same entity, maybe we can use this kind of signal to learn that Barack Obama and Mr. Obama are actually the same entity, right? So we try to exploit this kind of structural context, right? So we try to create these type of graphs by extracting this noun phrase and the relationships among them, and then try to learn some embeddings over them, right? So this is kind of how high level this SESI architecture is. First, given the documents, we create this what are called this open knowledge graph, and then we try to learn some embeddings for the nodes in this open knowledge graph. And then we finally do some sort of clustering to bring together related noun phrases and relations to individual clusters. And In addition to doing this kind of like graph embeddings, we also influence that embedding step by utilizing some side information. For example, you may have some expert inputs available which says that like, hey, these two noun phrases should be same. So we try to incorporate those type of additional signals in the representation learning phase while going from the graph to the vector embeddings. This source code is available at this URL, and you are welcome to give it a try if you're interested. So what we find is that by doing this kind of graph representation learning and then doing some clustering, we are able to improve on this canonicalization task. And in fact, before our work, which is given by this red line, this IDF was the previous state-of-the-art baseline, and we are able to get significant improvement in performance. And here are some examples. So these high-dimensional embeddings that we learned for these different noun phrases, we projected them in some 2 dimensions. And the way to read this is the noun phrases that are close by to each other. So we think that they should participate in one cluster. So we are able to learn some interesting patterns, like learning GSK and GlaxoSmithKline is the same entity, or that Sakyamuni and Gautam Buddha are the same entity, right? So this is interesting because on surface, these entities or these noun phrases look very different. And then if you would apply some sort of edit distance, they would look very far apart. But since we are utilizing this kind of graph context, we are able to bring them closer together. So this is the first task about one doing graph representation learning using one class of methods. Then along with resurgence of deep learning, there are also a lot of work on using deep learning over graph structured data. And one of the prominent methods in that space is what are called this graph convolutional networks, or GCNs, which essentially tries to learn embeddings on the nodes or vectors on the nodes by taking the immediate neighborhood of that particular node in the graph, right? So it's kind of tries to look at, apply some sort of composition operator on the embeddings of its neighbors, and then tries to refine its own embeddings so that it can do a particular task, maybe whatever node classification task well at the end of the day, right? So I'm not going into the details of how GCNs work, but we gave a tutorial on this topic in MNLP 2019. So all of the slides are available at this URL, so you can go and pursue this further. So in GCN related work in our group, we have also worked on how we can apply GCNs for knowledge graphs. So in particular, multi-relational graphs, where there are many different types of relationships on the edges. So if you just apply the vanilla GCN model on this kind of multi-relational graph, then it results in parameter explosion. So we have some work published in ICLR this year called ComGCN. So that tries to apply GCNs for knowledge graphs and multi-relational graphs, but being in a parameter efficient manner. Open knowledge graph embeddings that we just kind of talked about for the canonicalization problem. So we have also explored how we can utilize GCN style methods to solving those kind of problems better. So this was a method called CARE, which was published in MNLP 2019. So far, the graph embedding work that I have described, so all of them are operating over individual nodes, but many times you want to learn the embeddings on the whole graph. So you want to have a single vector that describes the whole graph, but potentially starting with vectors that describe individual nodes in the graph. So that's called as the graph pooling problem. So we had a method called ASAP, which was published in IIII 2020, where we learned this kind of representation at the graph level, starting with node level embeddings and vectors. And this kind of graph pooling is important because, for example, if you have a crystal structure or a molecule structure, which is nothing but a graph, and then you want to predict some properties about those, say, that crystal structure. For example, what is its formation energy, band energy, or what are like some molecular properties of that particular molecule. So in that case, you want to learn a succinct representation in the form of a vector, say, for the whole graph, and then so that you can make those additional predictions on top of it. And everything that I've talked about so far involves edges, which are binary. So one edge connects only two nodes, but then there are lots of problems where a single edge could potentially connect multiple entities, right? For example, if you have like a bomb blast event, then there will be like a perpetrator, there will be victims, there will be location, then there is time. So all of these things are connected by that single edge. So hypergraphs are a natural way to represent those kind of events and relations which have multiple arguments beyond two. So we have also done work on extending GCNs towards these hypergraphs, which we call as Hyper GCN, which was published in EWISE 2019. So these are just to give you some flavors of GCNs or graph neural network methods applied to various settings and various types of graphs. Now coming to the third part of how we can utilize these kind of learn embeddings in different tasks. So the first problem I would like to highlight is the problem of word sense disambiguation. So I don't know whether you have realized, but we humans kind of take natural language as granted. But when I come across a sentence like he wore a vest and a tie, this word tie could potentially have actually multiple meaning, right? So this could be tie in the sense of a necktie, right? That's kind of like a clothing component, or you could have like a tie in the sense of a football match being tied, right? And then you could also have like a tie as in connect, make a bond. So it's not clear immediately which one of these three senses we are referring to. I mean, from an for an automated NLP or NLU agent. But here, of course, tie, we are referring to this clothing item here, right? And by utilizing this context, we will be able to make the distinction, humanly. So the word sense disambiguation problem is how we can automatically do this kind of disambiguation. So this was a work called EWISE that it was published in ACL 2019. So what we were able to show that for doing this kind of zero shot or word sense disambiguation, if we incorporate external knowledge, which in this particular case in the form of lexical knowledge, then we are able to improve performance on this task, right? So I'm not again kind of going into the details of this, but what we are able to show is by kind of by incorporating this kind of additional knowledge. So this is our EWISE system, so that it's able to outperform other systems, even if it's when it's using 50% or half of the amount of label data that are being used by this other supervised system. So this is, and then when you use the 100% of the training data, then you do even better, right? I mean, this is a really hard task, and for a long time, the performance was kind of still hovering between the 65, 69 performance range, but we were able to demonstrate by utilizing external knowledge, we are able to do better on this particular task. Another task is around question answering, right? So given a question like who starred in other films made by the director of Titanic, right? So in order to answer this type of questions, if you have some underlying database or a knowledge graph, so you could say that Titanic was directed by, say, James Cameron. James Cameron also directed this movie Avatar, and Joe Saldana acted in that particular movie, right? So we can potentially answer this question by doing this 1-hop, 2-hop, 3-hop analysis or reasoning over this graph. But the problem is that most knowledge graphs in the real world are sparse. So in that case, maybe this dotted edge is actually missing in my graph. So I have to take a detour and maybe utilize even longer path to answer this same query, right? So instead of a path of 1, 2, and 3 hop, now I have to do say 1, 2, 3, 4, 5 hop reasoning over this graph, right? So that creates additional problems, and previous methods like GraphNet and FullNet kind of utilize additional text or some neighborhood restrictions, which created some additional problems for this particular task. So we propose Embed KGQA, where we learn some sort of embeddings for the question, which is in natural language. By utilizing one of the knowledge graph embedding methods, we learn vectors for the entities. And then we have some sort of a scoring function, like I was kind of describing earlier, which brings together this question and these entities together to finally come up with the right answer, right? Again, I know that I'm going quickly here, and I don't expect you to understand all of these things, but this is just to give you some flavor of interesting applications and methods in this space. So what we did was, so the Meta QA is a data set involving movie question answering. So compared to these other baselines, we see that even when the methods are quite mature, say even at 91% hit set 1 precision, we are able to improve on top of that 94 to 94.8. And this is the gains are especially pronounced when you have a sparse data, right? So sparse knowledge graph. So in this particular case, 50% of the edges were actually dropped from the graph. So we are able to see about 11% absolute boost in performance in this particular case. So this is demonstrates that by using these kind of graphs and learning embeddings over them, and then we can, through this combination, we can do better performance on these important tasks like question answering. Now, one more interesting task is around how we can combine knowledge and vision. So most of the tasks that I have talked about so far involving bringing knowledge and text. So one question is how we can, what we can do in terms of vision. So given an image like this, there is a task called visual question answering, or VQA. So you'll be able to ask questions like how many people are there in this particular image, right? So while that's helpful, that's not the only type of question I would like to ask about this particular image, right? For example, I would like to ask questions like, I know this is Barack Obama, this is Elizabeth Warren, but I don't know who is this person standing to the left of Obama in this image, right? Or are all of them politicians? So in order to answer those questions, while the content of the image is helpful, but that's not sufficient. So in that case, if we know about the identities of these entities that are present in the image and how they are related to each other in the graph, then maybe we can answer it better. For example, I know that this person is his name is, say, Richard Cordray, that's present in the graph, and then all of their occupation edges end up on the politician nodes that are yes, they are all politicians. So we call this as the knowledge enabled VQA or KVQA. So which kind of requires you to do deep learning and reasoning both over the image and the graph, right? So and we have also published a data set for this, which involves around 24,000 images and 180,000 QA pairs of this kind, which will require external knowledge and reasoning over them to answer them correctly. So this is, in short, that learning needs context, and knowledge graphs of various forms, factual, syntactic, temporal, can provide that context. And we right now have methods to embed those kind of graphs in continuous space and then utilize them in deep learning methods. And I have shown you some evidence that incorporation of that type of external context and knowledge can help improve performance of deep learning systems. So I know that I'm running out of time here, but very quickly, in the natural language understanding group at Google Research Bangalore, we are looking at how we can scale NLU to the next billion users, right? Which also includes India. And one of the problems we are looking at is the problem of multilingual learning. So as even if you take like the Indian society, so we are hugely multilingual. Like, there are like 122 major languages, only 10% of the population speak English, right? And most of us are like bilingual or trilingual in nature. So how we can build like robust computational models to kind of like facilitate learning, facilitate communications among people, and also between AI agents and humans. So there's like lots of opportunity and like lots of potential for impact. So so we're really excited about that. And then also like these kind of like multilingual societies throws up additional problems like we switch languages from one to the other. So how we can like build the models that are robust to those kind of phenomena like code mixing, code switching, and all. And then the second one is, which is probably no surprise given the background that I have been talking about, how we can also make advances in the area of knowledge graphs and how we can utilize them to improve NLP. So yeah, so that's all I had to say. Sorry, I think I went overboard a little bit, but if there is still time, I'll be happy to take some questions. Arun, maybe.
Yeah, sure. Thanks, Partha, for the great talk. I just picked a few questions from the audience.
Sure.
So here is one. So how are these different from ontology mappings?
Yeah, so ontology mapping, I mean, there is kind of like an ontology, and then I guess like the mapping is on top of that, right? I mean, the need for knowledge for AI has been kind of like long recognized, and yeah, and like people started doing kind of like these ontological approaches primarily based on kind of like manual efforts. So so yeah, I mean, ontology you can think of as like say a well curated version of the knowledge graph that I've been talking about. I think like the difference is one is kind of like about the representation, where they are kind of like I mean, very related. But I think like the more emphasis is on kind of like how do you build those type of graphs, right? So while a manual creation is one way to get there, but that's not always very scalable. So some of the efforts like NEL that I was talking about earlier is looking at like how we can do some of that work automatically towards like building these kind of knowledge repositories. So I think at a high level, the motivations and inspirations are very similar, but just kind of like how do you build these kind of resources beyond crowdsourced or human input based.
Sure. Okay, so one more question. So what kind of infrastructure is typically needed to train these kind of models?
Depends on like I mean, how much what's your scope, right? For example, if you take like the NEL system, so that was that had about like 1,000 predicates, and each predicate by predicate I mean like different types of knowledge. For example, like say person or mayor, or person will be say one predicate, city will be another predicate, and mayor of relationship will be another predicate. So it had about like 1,000 of those, and for each one of those thousands, each one of those predicates, it had about like 10 different machine learning algorithms that were working behind the scenes, right? But all of that could be done like say on some reasonably resourced server over say like NEL cycle was about like say 2 to 3 days, right? So I mean, if you're using like I mean like deep learning models for this, then of course like you will need some sort of like accelerator support like say GPUs, TPUs, and all. So yes, I think it depends on kind of like the scope of what's your coverage, how much like unlabeled data you are trying to process.
Sure. Thanks for the answer. Maybe quickly one more question.
Sure.
So how can you use knowledge graphs for speech-related applications? And if so, are there any applications?
Yeah, absolutely. So I mean, like I mean, the more broadly you can think of as like knowledge graphs, like providing context, right? And you can think of like bringing in that context using knowledge graph or like external sources, right? So it could be like many form times. Like one example is like say iodine, like iodoform, right? So I mean, you have like some. I'm just giving kind of like a very specific example here. So if like maybe kind of like you misheard, right? I mean, even as like manually when we are talking to each other, we may kind of like mishear something. But if we kind of like utilize that context, right, and our knowledge about the world, then we can like use it to like correct some of those errors. So sorry that I don't have like a ready-made example right now, but I think there was like an effort called like never-ending listening or never-ending like speech learning or something like that, which was trying to do similar to what like Nell was doing. But in general, I think that's a very promising area, and that's something we are actively interested in, even at Google Lab in Bangalore.
I guess in the interest of time, we can stop the questions. Thank you. Thanks a lot, Partha, for the excellent talk.
Yeah.
Thank you very much.
Thanks for having me.
Sure. Thanks. Okay, so the next talk begins at 3:45 p.m. So we have 10 minutes break. So what I'm going to do is I'm going to send a link for the poster session, which I mean, these are some of the posters that students at IITM and RBCDSAI have created based on their work. So let me first send that link out to everybody in the chat window. You can take a look, and I'll flash one or two videos that the students have made on their work before we get started with the next talk. So I just sent the link for the posters for day one. So there are 4 posters, and what I would do now is pick one of them and play the corresponding video for the poster. So this is work by Harshavardhan Kamarati, and here is a video that he has made for us. Let me start that for you.
Is motivated by the problem of infused maximization. But the goal is to pick a small subset of nodes to activate, and this activated nodes in turn diffuse the information along the edges, and once the process reaches equilibrium, the goal is to maximize the number of influence nodes in the entire network. So in the real world, we don't have the information of the entire network, and in collecting this information, we introduce a problem of network discovery where we have a very small subset of the graph called the initial graph. At each iteration, we query one of the nodes in the discovered graph to include the neighborhood of the queried node. And this process continues until we have some budget, and then we perform infused maximization in the discovered graph. Since this is a sequential addition problem, we use reinforcement learning where our RL agent takes in the current discovered graph as a state and picks the next node to be queried from the given graph. And after some fixed number of time steps, we terminate the episode and receive the reward as total number of nodes which have been activated after infused maximization on the discovered graph. We observed a 727% improvement over previous state-of-the-art graph sampling methods, and we also noticed that the TQN uses useful properties such as degree centrality and between centrality to pick optimal set of nodes.
Okay, so that was a video. So the video is also available in the link that I sent. So in case you are not able to clearly hear the video, what I shared, you can go to the link and also check the video. So before we start the next video, so a couple of high-level announcements. So if you have any admin-related or logistics-related questions, please email events@rbcdsai.org rather than asking them in the Q&A here. So let's all use the Q&A here mainly for technical questions to the speakers. And I also encourage the participants to upvote certain questions that you think are interesting and you want the
speakers to answer for you, so that it becomes easier for the speaker to pick and choose questions as well. Okay, so let me now share the second poster for the break session. So this is a poster by Tarun Kumar. Again, you have much more details about the poster, the work, the code, everything in the link that I sent. So I'm just going to play the video that Tarun has created for us. So here is the PDF, for instance, if you wanted to take a look at it. Yeah, so let me play the video. Again, the video is also available in the link for you to later check as well.
Hi, I'm Tarun Kumar, PhD student at RBCDSAI, and my work is on defining hypergraph model. Hypergraphs are a generalized version of graphs where an edge can connect multiple nodes. In hypergraph literature, we call them hyperedges. Very similar to graph clustering, the problem of hypergraph clustering is to find densely connected components in a given hypergraph. The problem generally arises in many areas, such as component placement in VLSI, where the goal is to come up with a schematic such that minimum buses should cross each other. In image segmentation in computer vision, where the aim is to cluster the pixels such that within a segment, pixels should be more similar as compared to cross segments. Similarly, in biological systems, you may need to identify modules responsible for some disease, or modules that respond to similar drugs. In the absence of such hypergraph-based clustering methods, one falls for graph-based clustering method and loses the critical higher-order information present in the underlying system. In order to do hypergraph clustering, we made the following contribution. We proposed a graph-based null model that can preserve the node degree of hypergraph. We also introduced a graph reduction mechanism that will preserve the node degree of the actual hypergraph in the reduced graph. We defined this null model because it is a crucial component for using a very famous graph clustering algorithm known as the Newell algorithm. After finding clusters with the Newell algorithm, we proposed a further refinement procedure that can define the clusters that will use the previous step, where we also highlighted the need to get balanced hyperedge. To understand
Okay, so with those two posters, I will stop my share.